Hello, and welcome to Ensuring Spacecraft Reliability, the critical role of material properties and challenges of radiation effects in industry, an EMA Expo 2025 event. My name is Matt Colding, and I'll be your host for today's presentation. Today's session will consist of two presentations, each with a Q&A portion. Please be advised that to submit any questions you have during today's webinar, you can use the Teams webinar Q&A feature at the top center of the menu bar. After each presentation, we will address any submitted questions. If there are any questions that remain unanswered by the end of the webinar, we will address them via email. Our first speaker today is Nicole Potier McGillivray. Nicole is the owner and chief engineer of Carrington Shield Strategies. Nicole specializes in spacecraft charged particle interactions. With expertise in radiation effects and spacecraft charging, she's contributed to many diverse platforms. Nicole holds degrees in meteorology, climatology, planetary science, and atmospheric, oceanic, and space science. She joined the industry in 2015 at Electromagnetic Applications, transitioning roles at Seeker Engineering and Maxar Space Systems in 2018 and 2022, respectively. Nicole then founded Carrington Shield Strategies in 2024, for which she serves as the owner and chief engineer. CSS was founded to provide the aerospace community at large with consulting services in space environment effects. Thriving on challenges, Nicole passionately solves complex problems in the aerospace industry. We are proud to welcome Nicole as our first expert presenter during today's event. Without further delay, I give you Nicole.
Thanks, Matt, for that introduction. Can everybody hear me okay?
Audio is coming through great.
Great, thank you. Good afternoon. I am Nicole Potier McGillivray. I will be discussing today the radiation hardness in the new space era. So first, just to kind of expand an introduction, I have about 10 years experience in the space environment effects on spacecraft systems and vehicles. My primary area of expertise is in the charged particle environment, so electrons, protons, and heavy ions, specifically in their internal and external effects on spacecraft designs, including effects both due to radiation and spacecraft charging. As Matt mentioned during the intro, I founded Carrington Shield Strategies in 2024 to expand my reach into the aerospace community. I'm finding, especially in the current challenging times, I am able to support different entities as needed. And it's also easier as a shop of one to adjust to changing times, such as the birth of new space. Fun fact, my company is named after my son, Carrington McGillivray, age 5. And yes, he is named, in fact, after the Carrington event because I am that big of a nerd. Okay, so first I'm going to go into some motivation and background. What is radiation? Why is it there? Why do we care? I'll discuss what I mean by the term new space. I'll review some current progress in the radiation effects community as far as adapting traditional radiation hardness assurance programs, or RHA, to changing times. And then I'll introduce something that I'm calling the menu approach, and I'll explain more what that is. And I will go ahead and walk through a real, real fake mission demonstration to show kind of what the differences are between the traditional RHA versus the menu approach. And then I will conclude. So I'm going to take a chance that most of the audience knows that there generally is a space weather or solar cycle. Space weather is correlated with sunspots, and we can measure the number of sunspots as a function of time. So this figure here is from the Space Weather Prediction Center website, and it shows the number of sunspots throughout the last 7 decades. So you can see we reach kind of a solar maximum and a solar minimum in each approximate 11-year period. And we are currently sitting at solar max for solar cycle 25. And this is relevant because it plays into radiation effects. There are three fundamental sources in near Earth space. So I'm going to kind of go through each one here. The first is intergalactic in origin. So these are in the form of galactic cosmic rays. These are highly, highly energetic particles that tend to penetrate through most things. And they originate from outside of our solar system. The second fundamental source is from our sun in the form of solar particle events. So this is generally referred to as space weather. So the sun literally will burp up these storms in the form of coronal mass ejections, CMEs, solar flares. And these events are modulated by galactic cosmic rays. So as space weather or the solar cycle becomes more active, the contributions from particles from galactic cosmic rays tend to decline and vice versa. So when we're during solar minimum, we get a larger contribution of particles from galactic cosmic rays, and when we're during solar maximum, we get a smaller contribution. So they're interconnected. The third fundamental source are the trapped radiation belts. So most know that there is an inner belt dominated by protons and an outer belt dominated by electrons. But during particularly large events or geomagnetic storms, we sometimes get an intermediary transient belt. The trapped belts are intimately related to the Sun-Earth connection. So when conditions are right, the magnetic field from the sun actually connects to the magnetic field lines of Earth. These newly connected magnetic field lines are then transported into the magnetotail behind Earth, at which point they then reconnect on the night side of the Earth. So the particles that were all kind of frozen in flux or trapped on magnetic field lines now are input into the Earth's magnetosphere system. And then they gyrate from magnetic north to magnetic south pole on Earth's magnetosphere, and they kind of are stuck there. And that's how the particles in the radiation belts get there in the first place. So as you can see, these three things are intimately related, and they're strongly connected to the solar cycle. Okay, so why does that matter? So what are these particles doing? There's a couple different kind of blanket umbrellas of radiation effects. The first being total dose. And total dose includes both total ionizing dose or enhanced low dose rate sensitivity, which is the same thing as TID, just at lower dose rates, and then displacement damage dose or total non-ionizing dose. And these effects are cumulative in nature. So think I need to put sunscreen on because I'm constantly exposed to ultraviolet radiation when I go outside. And over the course of my lifetime, I will accumulate more and more UV radiation. This is similar, except it affects microelectronics. And what kind of effects you might see in your microelectronics as you accumulate more dose is you'll start seeing your different electrical parametrics start degrading over time. So electricity doesn't quite flow the same way it once did. And eventually, after enough dose, the part might cease to function depending on its sensitivity levels. The second fundamental umbrella of radiation effects is single event effects. And these are more transient in nature. So you have a unlucky heavy ion or something that strikes the sensitive volume within your microelectronic device and causes some sort of upset. There are two sub-umbrellas under single event effects, and that are non-destructive and destructive. So non-destructive literally is a very temporary thing. You can have single event transients, upsets, something called a single event functional interrupt, which basically throws your microelectronic into some unknown state. So then it needs to be power cycled to be reset, just like turning on and off your computer in order to regain functionality. You can also get bit upsets in your memory devices. So that's something that can be rectified by rewriting the memory often or using some sort of error detection and correction code. Destructive events are obviously more concerning as they sound because it's usually caused by a single heavy ion, but it causes some sort of destructive mechanism within your device, basically rendering it useless. Once it's bricked, so to speak, or latches up or burns out in space, there's no fixing it. You can do things to kind of mitigate some of these effects, but ultimately it does come down to screening your devices before you integrate them into your design to ensure that you're not taking on more risk than you desire. Okay, so this might be kind of self-explanatory, but it comes up a lot in my experience. Radiation effects are best to prepare for early in the mission. So in the early design phase of a mission, it is critical to start thinking about your space environment because late discovery of problems due to radiation effects leads to drastic increase in cost and often hits schedule as well. Often radiation experts get pulled in kind of into a mature design situation, and these again end up being a lot more costly to deal with. Okay, so now I'm going to kind of segue into new space because I think what I just said about the preparing for radiation as you are in the early design stages is extra critical for things like new space. So what is new space? This plot or figure here is showing orbits around Earth. So you can kind of clearly see that large far out orbit, that's geostationary orbit. And then you have a wide variety of others in between. But then the big white sphere in the middle are LEO orbits, low Earth orbits. And it's getting quite crowded there. So one of the best definitions I have found of new space is the primarily commercial companies whose goals include achieving low-cost access to space at unprecedented development speeds. For those of you who have mustered the strength to make it through a grad school program, there's this idiom that is discussed a lot in graduate school in which you have a social life, good grades, or enough sleep, choose two, and you give up the third. Similarly, in new space, you've got low cost, fast schedule, and low risk, pick two. Most often for new space companies, the risk is the toggle. So they accept a lot more risk than traditional space programs. So to further illustrate this point, these charts are representing kind of the characteristic red, yellow, green risk matrix that a lot of program managers like to use in aerospace. So on the y-axis, you have likelihood of occurrence. On the x-axis, you have impact. And for old space, there's like an orange dashed box on the figure on the left that show it's kind of hand wavy, but the area of comfort that a lot of program managers in traditional space or old space like to live in. So the scales of impact and likelihood go from 1 to 5, 1 being unlikely or it's an inconvenience really, to 5 being it's almost guaranteed to occur and it's catastrophic in impact. For new space, that fundamentally changes, and the window of reasonableness for new space is quite a bit bigger. So you'll see perhaps an impact all the way up to 3, and a likelihood of, yeah, it's pretty likely to happen is acceptable in many cases. To further demonstrate here kind of why this is such a big issue now, this plot is showing the US commercial space launches from 1990 to 2023. And you can see here in 2023, there was 117 commercial spacecraft launches, many of which were due to SpaceX's Starlink, but there are many other entities that are getting involved. And clear guidelines and standards regarding updating the radiation hardness assurance programs are kind of they're struggling to keep up. The traditional RHA programs are usually cost and schedule prohibitive for many commercial space companies. There have been some attempts quite recently to close some of these gaps by providing less expensive approaches to part selection, radiation testing, radiation environment modeling, and best practices, which I'll discuss in a little more detail momentarily. But many of these attempts often assume budgets and schedules that are not commensurate with many new space programs. The design cycle for a lot of these new space programs are on the order of months, not years. So radiation testing alone presents a significant issue in the traditional RHA approach. Fundamentally, it can take months to obtain heavy ion beam time with the current demand on the few cyclotrons in existence. If I'm not mistaken, I believe there's only about 7 globally, 4 of which are in the United States, and the entire radiation community is vying for the same beam time. So this is a pretty critical issue. So one of the most pivotal papers that's kind of been circulating in the community for quite some time is from Sinclair and Dyer 2013, who coined the term careful COTS, COTS being, of course, commercial off the shelf. This emphasizes part selection and strategic testing in order to minimize catastrophic risk, with a big emphasis on the catastrophic risk piece. So the focus is on screening for destructive single event effects and TID, so that dose effects, basically weeding out parts that really have a low or have a high sensitivity to these effects, and trying to find things that might be a little more robust. A lot of this work, and this is documented well in the paper, can be approached with a proton beam instead of a heavy ion beam, but there are a lot of limitations to this. The secondary ions that are produced during a proton beam test only reach linear energy transfer thresholds, or LET values, up to about 15. And the real space environment, you have heavy ions that can impart much higher LETs into your equipment. An LET, apologies for not throwing a basic slide in here, is basically a measurement of how much energy is imparted into a medium by a particle. So it's a fairly complex thing that matters on the atomic weight of the particle and energy, etc. So proton beams can determine if there is a very high sensitivity to like a destructive mechanism, but if something passes at a proton beam, it doesn't guarantee it will pass in heavy ions, and that's kind of the weak link there. The other thing that Sinclair and Dyer 2013 really emphasized is a clear system level design techniques to improve overall availability and reliability. And there are some really good pieces of information in this resource. Campola and Pellish 2019 also highlighted that existing RHA flows and processes do not need to change, but risk tolerance and acceptance levels do. Which in my experience, I 100% agree with, that the biggest toggle that new space companies tend to play with is the risk tolerance. During the traditional RHA approach, a lot of companies in traditional space require what is known as 4 nines, where they're looking for you to mathematically prove that you have a 99.99% probability of success for your mission, of which radiation assurance is one piece of. And for new space, that is not a thing. So risk tolerance, all of a sudden, we don't necessarily have to be on the right line of conservative anymore, because failure in this case can be an option. The NASA Engineering and Safety Center also put out a report recently via Hudson et al. 2022, Section 7.2.94 of which states that the ways in which a program may pursue an acceptable radiation risk level is dependent on programmatic and technical considerations of the program, meaning that it is up to the programmatic team to consider all of the constraints of a program: cost, schedule, risk, and mission intent, to decide how to handle radiation. Which leads me to a pivot. So the MENU approach, MENU stands for Mission Essentials New Utility. And basically it's an idea that allows decision makers to determine the appropriate building blocks of an adapted RHA program while considering the constraints of said program, meaning cost, schedule, risk, and mission objectives. So instead of that 4 nines where you have to have the 99.99% probability of success, the question becomes, what needs to be done to obtain a reasonable indication that the system level designs will function as intended in the radiation environment? How do we get there? We can use qualitative and quantitative items that aim to realistically estimate the risk, i.e. less conservatively. And then these become the specific menu items that a program manager or decision maker can select from. So this is showing an example of what maybe a menu would be for a given program. So going from left to right, I've got category, item, description, assumptions, and a time estimate. So in the categories, you may have things like reviews, characterization exercises, testing and analysis. For reviews, it's common to do a BOM review or a bill of material review, where we're looking for existing radiation data in the public domain for the list of microelectronics that may be in a design. For characterization, usually we're looking for some sort of environment characterization for a particular orbit. So I want to know, what is the linear energy transfer spectra from heavy ions and protons? And then what are my dose depth curves for my total dose effects? Testing is all sorts of different testing, including dose testing and single event effects. And then analysis would include analyzing test results or performing a single event effect rate analysis. Although I will say that for a lot of new space programs, soft errors, so like how often some computer may need to be reset due to single event effects, is less of an issue, and it's more the destructive risk of destructive events that the new space community tends to care about. Okay, so to demonstrate kind of what a menu program might look like, I've come up with kind of a fake. This is completely made up, but this is going to be our demo mission here. So we've got a small constellation of 10 commercial spacecraft, each containing a set of instruments aimed at making measurements of air quality on Earth in a mid-inclination, low altitude, low Earth orbit for 1 year. Out of 99 unique, potentially radiation sensitive devices that are in the design, 1/3 of them have flight heritage from the same company, and it's flown in other orbits, but no radiation test data. 1/3 has existing test data, and 1/3 of them has no data whatsoever. The launch date is 2 years away, with the critical design review being about 10 months away. And the company has budgeted $250,000 to address radiation. There are no strict radiation requirements for this mission. So for those of you who, that was way too many words, I've put all the summary of that in these two charts here. So first, I'm going to kind of walk through if we were going to approach this with the traditional RHA approach, what that would look like, and then I'll walk through the menu approach and we'll compare. For simplicity, I'm only going to focus on radiation testing. Obviously, analysis is a huge part of this, but in order to kind of keep on the apples to apples approach, I'll only focus on the testing. So a traditional RHA program would require radiation testing, both total dose and single event effects, for all of the devices that lacked explicit radiation test data. So 66 of the 99. And there likely would be a set of requirements in the traditional RHA approach that incorporates some sort of radiation design margin or RDM. And so this means, like, let's say I have characterized my environment. I think that my equipment is going to see through all the shielding 10 kilorad of dose. Adding an RDM of 2 on top of that means that we would need to obtain test data up to 20 krad. So the first point is testing, particularly for single event effects, is very expensive. So I took the liberty on Nuclear Space's website. They do a really hand-wavy estimate for how much for some single event testing. Results do vary, so don't take this as truth. You have to get a quote for your specific situation. But for the sake of this exercise, 3 part numbers at 2 LET points, which is bare minimum. Arguably, you want more points or better. Nuclean can do that amount of testing for approximately $10,000. So expanding out for, let's say, only 20 parts, 20 devices out of our 66 require single event testing. Excuse me. Reason why only 20 might be required is because there are parts like diodes that tend to be fairly robust against single event effects. So it may not be imperative to test those parts. Please. So assuming that we need at least 4 linear energy transfer points for non-destructive test, that would then translate to approximately $130,000. For destructive events, if you're just doing a screening to make sure that it's statistically low likelihood in your orbit, you might be able to suffice with just 2 LETs, and so that would cost around $65,000. Total dose testing compared to single event testing is relatively inexpensive. I didn't really have a good off-the-cuff resource here. So for the sake of this exercise, let's assume it costs about $850 per device to test. And these can often many parts can often be tested simultaneously. So then dose testing for 66 devices would therefore be about $56,000. So putting this all together, it's expected then for the RHA approach for this particular mission would cost just over $250,000, which would max out the budget, no analysis included. So stepping back and then looking again at what needs to be done to obtain a reasonable indication that the system level design will function as intended in the radiation environment. We know that 33% of the devices in our design have flown before. So there's some amount of flight data, on-orbit data. This is important enough, this asterisk here is important enough that I'm going to kind of completely derail myself and pause. This is an important note for new space companies. What can be done in the current mission to buy down future risk and future flights? What measurements can be taken in flight to observe and/or diagnose radiation effects in orbit? The ability to query the systems on orbit provides the commercial spacecraft company a significant opportunity for cost savings for future missions. So a little bit of extra data for a current mission may expand the usability of that design for future missions. So I will go into a little more detail about what I mean by on-orbit data, because it is definitely very different than radiation test data as a whole. And there is a tendency of these new space companies to be like, oh, I know this part has flown before and that's all they know. So I must be able to use it now without knowing for sure without even knowing from previous examples of how that part functioned in its design. And also the design configuration can make a difference as far as survivability comparing. So the orbit and the configuration of these devices on the previous mission may not perform the same way in a different configuration. So in this case of the on-orbit data, the beam was actually the actual space environment comprised of several different beams of varying energy, flux, and ions in real-life flight-like configurations. Usually with new space, the mission's not bound to any sort of performance upset rate. So it's okay for the system to temporarily go down due to non-destructive single event effects, for example. However, as with most space missions, catastrophic failures, like due to destructive single event effects, are usually a problem. So then we suggest here that we perform single event testing and total dose testing on the remaining 33 devices that have absolutely no test data and no flight data, which would have the estimated testing costs compared to the RHA example. So $125K instead of $250,000. Okay, so going back to that asterisk of on-orbit data. So the 33% of devices for our mission that have flown before, how can we make something useful out of this on-orbit data? Let's say this commercial space company didn't think about the future and then they didn't put any extra diagnostic testing or little ways of observing radiation failures. And let's just say they threw it up there to see what would happen. We can use a combination of publicly available and free measurements and industry accepted tools to kind of piece together a story. So in this case, we can approximate what the design saw on that previous orbit. GOES-R is in geostationary orbit and does measure particle fluxes in geo. Well, our orbit is LEO, so how is that useful? You can use tools in CREAM 96, for example, to propagate a real observed environment through the magnetosphere down to your whatever your orbit may be, to approximate a real environment that your design may have seen. A lot of people in CREAM, you have the ability to use more severe environments like a 95th percentile or something like that. But in this case, that does us a disservice. We don't want to see the most conservative environment. We want to see what the parts actually were hit with in real life so that we can make some sort of inference as to how they may perform in a different orbit. Similarly, SPENVIS has some free tools to approximate a dose depth curve in a particular orbit. And so you can approximate these spectra and total dose curves that the design may have realized in a previous mission. The same tools then could be utilized to approximate the new mission profiles. And then you can compare these profiles to make some qualitative approximations of the 33 devices with flight heritage. Now, of course, I did already mention that if your configuration is changing, so it's a completely different design, this is a bit hand-wavy because the real weakest link in your design, that something that performs is the most sensitive to radiation, isn't necessarily going to drive your whole mission profile because or your performance rather with respect to radiation. There's inherent like capacitance and other things in your system level design that may improve the performance despite that weak link, so to speak. So it is careful to kind of consider those things. I've estimated here that an analysis of using those tools may cost around 20K in labor hours compared to testing estimates of 125K on those 33 devices with flight heritage. But then here we're leaning on that risk analysis that is qualitative as opposed to the quantitative testing, the quantitative results we might get from testing towards that 4 nines, 99.99% probability of success. And for many new space companies, that becomes acceptable. Okay, so this is breaking down the menu approach. So the first subtotal corresponds to testing those 33 devices. The second the second and third subtotals correspond to the breakdown of the analysis costs. So characterizing the environments and then comparing the realized environments on the heritage design with the potential new environment for our current mission. So the total cost for the mission then for the whole bill of materials would then be around 145K instead of $250,000. Okay, well, schedule is often more important even in new space because we're talking about design life cycles that are on the month time frame. So that's equally, or if not more important, to compare. Again, our limiter is the single event effects testing. The screenshot I have here is of, I think, last month's, or actually, yeah, the first week of June's schedule from the Texas A&M cyclotron schedule. I did this analysis from the December 2024 schedule. I forewarn you, this is super hand wavy, but I'm trying to demonstrate kind of the approach here and inability to compare. This is a highly idealized schedule, I will say. So looking at the December 2024 schedule, they allotted approximately 360 beam hours, and those were available as a rolling every 3 weeks period. And approximately 18 groups were scheduled during the December 2024 window. So on average, that means 20 hours of beam time per 3-week window was granted per group. I estimate, kind of looking at the Nucleon website and my knowledge of the test campaigns that I participated in, that about on a very simple device, it may take about an hour per LAT to test. So if you need 4 LAT points for a non-destructive test for 20 devices, that's about 80 hours of beam time. 2 LAT points for a destructive test for 20 devices, about 40 hours, which means for the RHA, traditional RHA approach, you may need 120 hours of beam time and only 60 for the menu approach. So that means for the RHA approach, you might need a total of about 6 3-week sessions of 20 hours of beam time each, which is 4.5 months. Again, extremely idealized. In reality, this would make the differences much bigger. Similarly, the menu approach would be about 3 3-week sessions or 2.25 months, and throw in an extra half a month for that analysis of that heritage data. In addition to this already being a highly idealized estimate, I do think that more beam time might be granted to larger companies who utilize the beam more frequently. So that does also bias the situation. So based on this, the menu approach would cost roughly 60% of that of the traditional RHA approach, just considering testing, and would also take approximately 60% of the scheduled time. The trade-off again here is risk tolerance. So the menu approach emphasizes risk reduction as opposed to a 99.9% probability of success. Another small asterisk here that's prudent to note, in both approaches, there is always the risk that is often realized that a device fails testing or performs poorly enough that an alternate has to be selected. And obviously that plays into this whole risk balance equation as well. Okay, so in short, the new space era has introduced uncertainty in the best approach to radiation hardness assurance due to primarily evolving risk tolerance postures. We've demoed here an example mission for a commercial program to show that a qualitative or pseudo-quantitative menu approach may be better suited for new space programs with significant programmatic constraints. In a lot of cases, the new space programs are so heavily constrained that they just decide they're going to throw something up there and not do any radiation preparation whatsoever. And what that means is if we're going to be having a lot of commercial companies placing items in LEO that are going to kind of fall back into the atmosphere very shortly afterwards, having some sort of program to reduce radiation risk may make a bigger difference from a sustainability point of view. In practice, the menu approach is highly customizable to fit each unique situation. It's been rare that I have met a new space program or company that is identical to a different one. And for this reason, I truly believe there will never be a one-size-fits-all approach for new space. And I very much agree with the previous work that's been done by the community to kind of close the radiation hardness assurance gaps in the presence of new space. I think it has to remain customizable, and that's kind of the whole point of this menu approach. Thank you so much for your attention. I am happy to take more questions now, if there are any.
Excellent. Thank you very much, Nicole. We'll now transition into the Q&A portion of this presentation for the next 15 to 20 minutes. As a reminder, all attendees are encouraged to submit questions to the team's Q&A feature during this time. So with that said, let's begin reviewing the questions that we've received. Looking at the first question, there's a question here. Are we seeing a similar trend in new space for solar cell technologies? These also degrade based on the radiation particle flux seen in specific mission orbit and affect mission power.
That's a great question. The short answer is I don't know. I think a lot of the companies I have worked with are more focused on their microelectronics at this point. But I do see that the solar array technology is a fundamental part of the design. So probably equally as important to make sure that they're robust enough. I do think the solar cell technology tends to be more dose affected. So there may be more options as far as designs that may mitigate some of the effects, and that may be why they haven't come up quite as much recently, but still a very important thing to consider.
Certainly. Right. Not seeing any more questions currently in the queue, so certainly do encourage the audience to ask them during this time if there are any. Let's see. I would have a question for you to continue the conversation. So CSS is really focused on practical and adaptive approaches to space environment challenges. So where do you see the biggest knowledge or practice gaps in the current aerospace community that you all are aiming to address?
Yeah, that's a great question. I see many, but perhaps a big one that comes to mind. I think we as engineers, especially in a niche field like EMI or spacecraft charging or radiation effects, really we wear a lot of hats, and we're used to pulling ourselves up by the bootstraps and thinking about problems from many different ways. And especially with EMI, when there are so many different shades of EMI problems. But I do think the community at large tends to underestimate the value of bringing in other experts that specialize in other things so that we can focus on those specific, the physics of the specific problems we deal with. So for example, software engineers are underutilized, in my opinion. A lot of the tools that I use on a day-to-day basis have been in use for decades, and they haven't adapted as much with the way times are changing. And I think if we got some software engineers that are some good ones to focus on our tools and how to do the modeling in better ways and how to really focus on the things that the community needs, especially the new space community, I think that the whole community would move a lot faster. We'd have more brains on the things, like utilize the cross interdisciplinary practices, if that makes sense.
Yeah, thank you very much for that answer. We've received a few more questions now. So, next one is, how would you approach board level heavy ion testing and qualification for RHA in new space?
If only. Um, to my knowledge, that is still something that's really limited. The spot sizes at a heavy ion beam are extremely small. So it's really not, with the current technologies we have, not super possible to do heavy ion at the board level. I am aware of some groups that are trying to basically change that and like look at different perspectives to address this constraint of heavy ion beam time. But I'm not super familiar with where they stand and how much progress they've made. So unfortunately, I think heavy ion board level testing is still not possible. Proton board level testing, that's a different story. And I do know a lot of new space companies are utilizing proton board level to get very cheap, cheap being inexpensive, kind of holistic views at their design to figure out what things might be the weak link early on. But again, there's a lot of limitations with proton, particularly when it comes to like destructive screening and stuff like that. So that's a good question.
All right, next question is, are optical components like cameras susceptible to radiation? If so, is it possible to shield them?
Yeah, so I didn't cover that in my talk, but the displacement damage, optical equipment tends to be fairly susceptible to the total non-ionizing dose, which can kind of cause coloring issues, and it's similar to TID that it accumulates over time. So yes, they are very sensitive to radiation. Now, in new space, it's predominantly low Earth orbit. So the levels are low enough at which it may or may not be a problem, but it's something that I would definitely look into. As far as shielding goes, for dose effects, shielding does matter and can make a difference. However, I'm not sure how that works for an optical for optical equipment, because a lot of the times if it's a camera or something, you need a clear field of view in order to take the imaging you need. So there are a lot of I've seen some clever approaches to some of that kind of thing. But for new space, it may be a lower problem just because the dose levels you're getting at that point are less intense, and your mission life tends to be short enough that you know, in geo, where the environment is a little more intense and you're up there for 10 to 15 years, that's a really important question. And it's not that it's not important for a 1 year Leo, but all of a sudden it may be small small potatoes depending on your orbit and stuff like that.
Okay, great. Next submission here says, thank you for the presentation. As you said, your cost and schedule analysis assumes that all devices pass. In your opinion, what is the typical pass-fail rate for commercial off-the-shelf devices?
That is a great question. I cannot predict the future, unfortunately. I think this would be a much easier job if I could. I'm trying to remember, there's a paper from a NESREC conference from the Radiation Effects Data Workshop, I think by Matt Allen. Might be getting the first name incorrect. I want to say it was 2019-ish. I'm thinking of the graph in my mind, but basically it's a pie chart that shows from a destructive single event standpoint, on the order of a quarter of COTS parts have a destructive mechanism and can be weeded out. And the problem is you don't know where your device might fall without testing it, unfortunately. There doesn't necessarily seem to be a relationship between like the part technology that it's built on or what kind of device, if you're talking about a memory device or a wide memory or an op amp or something like that, unfortunately. But the paper shows kind of a subset that was tested, a quarter had a mechanism. So 75, you may have a 75% chance that you're all good, but finding finding the one bad one is tricky.
Absolutely. Okay, next question is, what are your thoughts on testing electronics for lunar radiation environment? How can we extrapolate from current radiation data from GEO or LEO to a lunar environment?
To a lunar environment. What was the first part of that question?
What are your thoughts on testing electronics for a lunar radiation environment?
Yes. Okay. So lunar's tricky because you don't have, it's basically geo, except you don't get any shielding from the Earth's magnetosphere. So it's sticking out past the Earth's magnetospheric bubble, which does shield a decent bit, but then you don't have to deal with a trapped electron belt like you do in geo. But I would say the approach is probably pretty similar in that you're still going to be susceptible to heavy ions. You've got that stuff coming from the sun, and you've got the stuff coming from intergalactic sources. And you still have dose effects due to the same sources. So it really is no different, except the levels at which you test to might be different. So for example, I wish I had this as a backup slide. I apologize. A lot of times in the traditional RHA approach, there will be kind of seemingly arbitrary requirements with respect to SCE testing. Like, for example, you can't have any destructive, you can't have any devices that have a destructive sensitivity at LETs below 37 for LEO or 75 for high reliability GEO. And these levels kind of correspond to the flux spectra. If you were to look, and again, I apologize for not having a figure and backup to show, but if you were able to look at the heavy ion flux spectra as a function of LET from the natural space environment, you would see something that kind of dramatically drops off around an LET of 37-ish. That corresponds to an element, the iron element. It's called the iron cliff. And what this means is that your prevalence of iron in the natural space environment drops significantly compared to some lighter ions. So things that are heavier are a lot less prevalent. And so single event effects in particular is a statistics game. So if you say that I am, so the reason that these thresholds exist are to play into the statistics. For high reliability geomission that has to work, it may be extremely unlikely. You may see a particle that can impart an LET of 75, once every 100 years, but those programs tend to want to know that and just remove that as a possibility. Whereas a new space program operating in LEO, they play into the statistics that an LET of 37 is a much higher prevalence, but at 37, it's less prevalent than iron, which is a lot less likely to appear, if that makes sense. So the testing doesn't change for a lunar environment, but your levels of acceptance might, depending on the mission. I hope I answered that as desired.
Great. Next question here is, how important is it to have both testing proton and heavy ion to fully characterize a device?
Very great question. I'm going to emphasize the fact that whoever asked the question specified to fully characterize a device. You do both. It's important to do both. And I would argue heavy ion is more important. You can make some assumptions on proton sensitivity based on how it performed under heavy ion. You can't really go the other way. If I take off the fully characterized piece, then it starts depending a lot. I think Mike Campillo once said, a radiation engineer's favorite response is it depends. And I'm sorry to agree. In that case, it really depends on your risk profile, because if you can accept something bricking your design, well, then just do the cheapest thing, which is proton. You still get some value out of it. So, but if that's not an option, then it's probably fairly important. At least you might want to do a modified heavy ion or a kind of a wimpy, skimpy one where you're only doing a couple OAT or something like that. There's lots of different shades of gray, and it really depends on the whole context of the mission.
Okay, and there's a second component to that question, and forgive me, it's formatted uh,
No worries.
clearly, but how would you address if any component is susceptible to protons as well? Can you use profit to use heavy ion data?
Um, so I actually haven't used Profit, so I'm not sure I can really comment on that in a detailed way. But I do again think that it's difficult to, or not super conceivable to go, if you have heavy ion data, you can make some inferences at how it may perform in a proton environment, but not vice versa. The number of secondary ions that are generated during a proton beam test. So not only is it limited into LET, but there are very, very low fluxes compared to what would naturally be found in the space environment.
Okay, great. Seeing no other questions at this time, I think we can. Oh, I just saw another one pop up, so forgive me, we'll ask one more. Do we see new space approach in terms of risk posture affecting the risk posture for traditional geo applications, in this case, specific to RHA and testing?
That is a great question. Again, it depends. I haven't, I've been working a lot in new space in recent years, which is kind of why I've gained some trial and error expertise into this realm. I do have had a lot of experience working in the traditional space where you're working with programs that are, they have to work. So you can imagine like programs that may have to deal with like DoD relations or whatnot, get a more strict requirements, for example. And I'm not seeing the programs that designate and have from the get-go a strong set of requirements to dictate a more traditional RHA approach. I haven't seen those change. But I think that new space is becoming so prevalent now that the number of more traditional programs comparatively, if you have your percentage of programs that exist at all, new space is starting to take a bigger chunk. So I don't think that the traditional programs necessarily are moving to a new approach. I just think that the breakdown of the programs that are needing help addressing radiation, new space is taking up a bigger percent, if that makes sense.
Okay, great. Seeing no other questions at this time, I believe it's appropriate to conclude the first presentation of this session. As a reminder, if there are any lingering questions specific to Nicole's presentation that we did not address today live, they will be addressed via email. So please feel free to still submit your questions. But we will now turn our attention to our second speaker. As I introduce him, he will share his screen and open his presentation. So thank you again very much to our first speaker, Nicole, for that very enlightening presentation. Our second speaker for today's session is Justin Christensen. Justin is a staff scientist at EMA working in the Space Environment Radiation Effects Lab in Pittsfield, Massachusetts. Before joining EMA in September of 2024, he spent 6 years at Sandia National Labs as a technologist, where he developed atomic sensors for inertial guidance and electric field sensing. Prior to his tenure at Sandia, Justin earned his master's in physics from Utah State University, focusing on space environment radiation effects within the materials physics group. As an experienced experimentalist, Justin excels in automating processes and designing experiments to probe the details of how things work. His passion for building and learning new skills has led him to develop many hobbies in woodworking, PCB design, FPGA programming, and computing. Now, please join me in welcoming our second expert speaker for today's session. And without further delay, I give you Justin.
Thank you, Matt. Are you able to see my slide?
Yes.
Okay, awesome. Um, yeah, so thank you. I'm Justin Christensen, and I'm excited to be back in the world of spacecraft charging after, as he said, I took a 6-year break to study atomic physics. This is what I studied in grad school, and I enjoyed it a lot, so it's fun to be back. Let's see. My presentation isn't advancing. Let me see. Okay, there we go. So my presentation, I plan to talk about material properties and why we care to characterize them. I'll explain some of the different space environment interactions that we care about in terms of spacecraft charging, and then I'll give a brief overview of a bunch of different properties and how we measure them. I included this picture. It's a picture of the Missy 6 experiment that was put up on the International Space Station for a year. It's one of several experiments that NASA and a lot of international collaborators put together um, to understand the effects of space, the space environment on materials, and so it's kind of obvious that they care a lot about this topic, and I think there's been several talks already on this topic or related topics that we really need to understand how materials behave in space so um, we can design for that. So I have basically three main reasons that I see that are important for why we characterize materials. First of all, we want to make sure that our spacecraft are safe and reliable. It's obviously expensive to put a spacecraft up there, and so we want to do what we can beforehand so that we can have as little risk as tolerable. Um, so because of that, we want to make sure that the materials are selected so that they can function correctly in whatever application they're being used, and so that they'll be able to withstand the exposure to the solar radiation, harsh temperatures, and corrosion from things like atomic oxygen or sputtering from ions. The next reason is that we need to be able to predict charging behaviors. Spacecraft charging has been shown to be one of the leading reasons for failures or anomalies in spacecraft. And so it's important that we can predict how the different materials are going to charge when they're placed in their environment and do what we can to mitigate any risk of anomalies. And then the third reason is we want to make sure that they'll perform correctly over the life of the mission. So we know that radiation modifies materials, and so there needs to be attention paid to how well they'll perform over their whole life. So what we can do on the ground, I'm going to kind of focus on the testing, but there's a important interplay that needs to happen between simulation and testing. Um, we can do lab tests in a approximate space environment where we can control the energies and fluxes of different types of radiation, electrons, ions, photons, and try to mimic the environment as close as we can in that setup, so that then we can monitor the surface potentials and other behaviors of the material. Obviously, we can't perfectly match the space environment in a lab. The space environment is composed of a spectrum of energies for each different type of radiation. It has large temperature swings, and there's variations due to solar weather. So on top of this, it's also very useful to be able to do computer simulations where you can more completely define the environment and predict what will happen when the spacecraft is put up there. To go with that, it's important to know that your simulation will work and be accurate. So there has to be effort put into validating the simulation software that you use. This usually takes the form of trying to replicate in your simulation the things that you can do in a lab. And you can simplify it so that there's just a few energies of the particles you care about. And if you know what the material properties are well enough for the materials, you should be able to get results in your validation tests that match what you see in the lab. And then that should give you more confidence in the results of your full environment testing. There's a lot of different interactions that can happen with in the space environment, and this is probably not a complete list, but they are kind of grouped into ways that charge can be deposited in the material. So electrons here are shown in blue, ions are shown in pink, and photons are shown in yellow. And the incident ions and electrons can deposit negative charge in the material. The energy that they deposit can excite electrons and knock them out of the material. And that takes the form of what's called secondary electrons. You can also have electrons that come in, undergo several collisions, and then are re-emitted back into space. Those are called backscattered electrons. You can have photons that come in and deposit energy and knock out photoelectrons. And then you can also have modification of the surface due to ablation. Once you have charge deposit in the material, then what happens after depends on several different material properties. There's different types of conductivity that explain or describe how the deposited charge will dissipate over time. And if there's a relative permittivity of the material, which describes with a certain amount of charge that's deposited what the potential will be, and then how much energy is stored in the dielectric material. And then if the potential is able to reach a threshold, you can produce an electric field above the breakdown threshold of the material. And that's a property that describes when you'll start to see electrostatic breakdown that can damage the material or damage other components of a spacecraft. Not the last interaction I included on here is not directly related to cathodoluminescent, or sorry, it's not directly related to charging, but it's also a potentially important interaction for some missions called cathodoluminescence, which is where light is emitted from the material as it's being irradiated by electrons. So I'll move on to start talking about the specifics of these different properties. The first is dark conductivity. It's also just called conductivity or bulk conductivity. And this property describes how charge flows in a material when you apply an electric field. So if you have some block of material, there will be some amount of free charges in it that are able to move. In conductors, it's mostly electrons, so the negative charges that are able to move, and there's a lot of them. In semiconductors, you can have a combination of negative charges and positive charges, and the concentrations of those can depend on the doping when they're manufactured, and it can also depend on the temperature of a material. And then insulators just have a lot less charge carriers. When you apply a electric field, the negative charges will, I guess, the positive charges will go in the same direction as the field. The negative charges will go in the opposite direction. And the combined net charge that flows through a surface per unit of time is the current. So if a material has a high conductivity, it will have a lot larger current flow with a given electric field. It's kind of interesting, with metals, the conductivity usually decreases with higher temperatures because the vibrations of the lattice interfere with the movement of the electrons. But with semiconductors, it's the opposite. Higher temperatures usually increases the conductivity. A related property called the resistivity is also used a lot, and I apologize if I use both of those words interchangeably. Basically, if something is really conductive, it's not going to be very resistive, and vice versa. And the relationship is that the resistivity is the inverse of the conductivity. You can develop a simplified model for a material that's being charged and kind of treat it like a capacitor. Just parallel plates with the dielectric between it. And with a given relative permittivity, which I'll talk about later, and resistivity, you can predict a certain amount of decay time for that particular material that describes how long it takes for charge to dissipate once you've put it, once it's been embedded in the material. This graph has defined regions of safety versus issues with different decay times, and the cutoff between them is not necessarily solid. There are situations where a decay time that's lower might still not be adequate if the charging rate is high enough. But kind of a hand wavy explanation, you can say that if the charge can dissipate in less than an hour, then you're probably not going to accumulate enough to cause big issues. But if you have a high resistivity, then you'll start to have decay times months to years long, and at that level, it's definitely an issue, and it's hard to dissipate. To measure the conductivity, we use a constant voltage chamber configuration. And what that is you place your thin film of material between two electrodes, apply a voltage, and then you measure the current through the material. We have this picture of kind of that stack up. This is a look at the top electrode with the circular electrode and then an outer ring electrode that is used to help produce more uniform electric fields in the sample. It's important that these tests are done in vacuum if you're trying to measure the conductivity of something that's extremely resistive, because any contamination due to like water that's absorbed in the material can modify the results. Interestingly, if you monitor the conductivity over time with some of the extreme dielectric materials, you can see that when you first apply the voltage and calculate the conductivity, you get a higher conductivity than if you wait for a long amount of time. Oh, sorry. There are several different components to the actual model that fits this curve. And there's a bunch of different components that are time dependent and one that's not time dependent, and that one is the dark conductivity. And so in order to actually measure the true dark conductivity for extreme insulators, you can end up having to wait several days to collect enough data to finally get that asymptotic behavior. This is also interesting because it's sometimes hard to know what conductivity you should use when you see a graph like this. And that depends on your application. There are situations where if your environment is changing or if the voltage you're applying across the dielectric is changing on a shorter time scale, then you're never gonna come to equilibrium and never gonna actually see this type of conduction. So yeah, it's dependent on the situation. Here's just a view of the model that was used to fit that previous data and all the different types of corrections that you can account for. Moving on to surface resistivity. Notice I changed to resistivity. This is defined as resistance across a surface. So rather than looking at the current that goes through the bulk of the material, this describes how current moves across the surface. And this can be pretty different from the bulk conductivity depending on contaminations on the surface of a material and just the physics that are involved when you have the boundary of the lattice and a vacuum. You can have different types of, or different behaviors for conduction. The units for it are ohms per square, and that square doesn't actually have units, but it describes the general behavior that, like, if you have a square piece of, or I guess a square surface that you're measuring the surface resistance on, or resistivity, the as long as it stays square, the resistivity is about the same. But if you increase the distance between two contact points, that will double, like if you doubled the distance between two contact points, it would double the resistance. If you doubled the size of the electrodes that you're placing on, that would half the resistance. It's kind of interesting. I have this picture here just to show an example of where surface resistivity matters. If you look at the power lines outside, you'll notice that they sit on top of these insulators that have an interesting shape. And the reason that they choose this shape is because they want to maximize the distance that electrons would have to travel on that surface in order to get to the other side. So here you can see that in this test, they were doing a breakdown test to see what voltages they can reach before breakdown starts to happen. And the arc actually separates, and it's easier for it to flow through the air than it is to flow along the surface of the insulator. This is important, I think, obviously, because if your surface resistivity is much less than the bulk bulk resistivity, you can end up with more conduction along the surface. And so it's important to know all these different modes that charge can dissipate through. To measure surface resistivity, they use an electrode like this, where you have a center electrode and then an outer ring, and you place it on top of the material and measure the current that flows between that center electrode and the outer ring when a bias is applied to it. The last form of conductivity I'll talk about is radiation-induced conductivity, or RIC, and this describes how the conductivity can be modified when the material is in the presence of ionizing radiation. This radiation generates additional charge carriers in the material, and so when you have extra charge carriers, that means you can dissipate the charge more quickly. RIC can temporarily increase the conductivity in spacecraft materials, and this can allow the charges to dissipate more effectively. And it's related to why there can be drastic changes in the charging behavior of a spacecraft when it goes between the day and the night side of the Earth, and when the radiation environment changes. To measure it, it's pretty similar to the bulk conductivity setup, but you add a ionizing dose source. And the models that have been used to fit this relationship are power laws. So you could determine K and the exponent by performing fits to this data. If you look at the K values versus the temperature of a material, the K value you could think of as the dose when the conductivity when the dose is 1 rad per second. So if you increase the temperature, it makes sense that the conductivity goes up over time. Similar, you can look at the relationship between the exponent and temperature. And here it goes down versus temperature. And now I'll move on to the different types of electron yield. I'll start with photo yield, which is the production of electrons when photons impinge on a surface. Einstein discovered that light is composed of discrete packets of quantized energy, and the relationship of how much energy each packet has to the wavelength of the light is given here. So higher energy photons can deposit more energy in the material. There's also an interesting relationship that was found with when he discovered the photoelectric effect, that if you increase the energy of the photons, there's a threshold energy that's required in order to start freeing electrons from a material. And this energy is called the work function of the material, which is the difference between the vacuum energy and the valence energy of the electrons in the material. If the photon has more than this energy, then the electron can be removed from the material and the leftover energy is present in its kinetic energy. This has the effect of charging a material positively, and there's a limit to how much charging you can do with this, because at some point the sample will be charged positively enough that it will re-attract those emitted electrons. To measure the photo yield, there's several things that are necessary. First, you need a tunable light source, and so here's an example of one that we have been prepping to add to our capabilities in the SEER lab. It has a broad spectrum light source, and then it has this section, which is a monochromator, and that uses a diffraction grating that can allow you to separate and pick a small band of wavelengths that will propagate through and then be collimated and go out into the rest of the testing setup. You also need a vacuum chamber so that the deeper UV light can propagate to the sample. UV doesn't propagate very well in in atmosphere. And then you need a current detection system so that you can measure the current that's deposited in your material. You also need to be able to dissipate the charge that accumulates in your material. And then you need a computer or data acquisition system. If you look at the photo yield versus the photon energy, this is the number of electrons per photon. There's a threshold, like I talked about earlier, where below which the yield is 0. You don't see any emission. But once you cross that threshold, you start to see the emission, and then it increases with higher photon energies. This is two different materials, Kapton and HOPG, and you can see they have different threshold energies. Once you know this spectrum for your material, or this yield curve for your material, then you can multiply it by the solar spectrum if you want to know the total photo yield for the space environment. The next related yield, electron yield, is similar, but it's due to incident electrons rather than photons. There's 3 different types of electrons that are involved in these processes. There's the primary electrons, which is the ones that impinge on the material. Those undergo several collisions in the material, either finally coming to a stop in the material, or they can scatter around until they come back out as backscattered electrons. And then the energy that is deposited during those collisions can excite electrons from within the material. And if they are close enough to the surface, then they can migrate to and escape from the surface as secondary electrons. The yield that we define for electron yield is the ratio of emitted electrons, or I guess the average number of emitted electrons per incident electron. And there's corresponding yield values or yields for the backscattered electrons and secondary electrons. If you sum those two together, then you get the total electron yield, which is the total number of electrons that leave per incident electron. I also included this graph which shows the energy spectrum of the emitted electrons. So you can see that you have a low energy secondary electron peak, which usually peaks below 10 electron volts, sometimes even a lot lower than 10 electron volts. And then you have a higher energy peak that is centered at the incident beam energy. And so that's the backscattered peak. Between those peaks, the distribution doesn't drop to 0. And it's hard to define like a specific cutoff between them so that you can be sure that any electron above whatever energy is a backscattered electron or not. So in practice, most people have use a 50 electron volt cutoff energy, which works as long as your backscattered, or I guess as long as your incident electrons have energies above this. Oh, I'll also mention that this yield curve gives us a lot of information about how the material will charge depending on the incident energy. So if it's a yield larger than 1, then you can expect the sample to charge positively. If it's less than 1, you'll get negative charging. And at 1, there will be no net charging. And if you have an insulating material, as it charges up, that modifies the landing energy, and it can also reattract secondary electrons if that's positive charging. And so if you leave a sample exposed to a monoenergetic beam, the surface potential will charge up until you reach an equilibrium position or condition. And at that point, you'll have a yield of 1. So this curve can give you a lot of information about how it'll charge and what potential it will charge to before you get to a yield of 1. Here's a image of our what we call it the hemispherical grid retarding field analyzer, and this or HDRFA. You can see up here, this is our electron gun that we would use to fire our beam into this. And here's a cross section of that. So this is the beam tube that the beam comes through. And then that would hit the sample at the center of the grids. And then any emitted electrons are collected by the various elements inside the HDRFA. This outer element is a solid shell that we call the collector, which collects most of the electrons. And then we have 2 concentric mesh grids that can be used to produce equipotential surfaces inside of the HDRFA. They're mostly transparent, but that ability to bias them allows us to discriminate if we want to. We can apply a negative bias to this outer grid relative to the inner grid. And so only electrons with kinetic energy above that bias would be able to get through to the collector. That allows us to take measurements of this, like the spectra that I showed you on the previous slide. The last thing that we need in order to calculate the yield is to be able to measure the current on each of those different elements of the HDRFA. So this is kind of a explanation of our wiring schematic and how we can bias the different components. If you're measuring the yield of a conductor, it's pretty simple. You just use a steady electron beam and measure the steady current in each of the different elements. But if you need to measure the yield of an insulator, you don't want to, it's hard because the act of measuring the yield modifies the surface potential of the material, and that will in turn change the yield of the material. And what we want is to be able to measure the yield of an uncharged material. So we use a pulsed beam for insulating materials, and then we end up integrating over the duration of the pulse in order to determine the total amount of charge that was deposited in each of the elements. Moving on, ion yield is similar. It's the yield due to the impinging ions. And the main differences between the ion yield and electron yield is that you can deposit ions in the material, which can have either positive or negative charge depending on the ion species. Also, energetic ions can sputter the surface of the material, so that can change, that can remove material, and it can change the surface roughness, which also would modify the electron yield and the photo yield. I'll just glance over this. Here's a example of an ion gun, and to measure the ion yield, you'd use a similar setup to the electron yield with the HDRFA. And there's some information about the models that can be used to fit that data. The last property I'll talk about here is the relative permittivity. And this describes how when you apply an electric field to a material, the trapped charge inside will respond to that field. So without an electric field, all the nuclei in the material will sit kind of symmetrically in the center of their own cloud of electrons. But when you apply an electric field, that will pull the positive nucleus one direction and pull the electrons the other direction. And this stretching type behavior can store extra energy within the material. The higher the relative permittivity of a material, the more displacement is able to occur when you apply that field. And this actually screens the internal parts of the material slightly from that applied field. So the field inside of the dielectric will actually be weaker than if you were to remove that dielectric and measure the field in the vacuum. This property also can be used to relate the amount of charge that has been deposited on a material to the surface potential of that material. There's a real part and an imaginary part to the permittivity, and they're frequency dependent. So the real part describes how energy can be stored within the material. At low energies or low frequencies, it's pretty flat. But then at higher frequencies, it typically fall off. And if you look at the imaginary part, then this describes the energy loss mechanisms. And this is kind of related to like microwaves, where if you apply a microwave of the right frequency to your material, for example, water, it's at a specific frequency where it's able to induce resonances in the water molecules. And those resonances convert the incoming electromagnetic energy into thermal energy in the material. To measure the relative permittivity, there's a lot of different methods, and they all have different benefits and drawbacks. The simplest is probably just to use a parallel plate capacitor setup, where you just place the material between two parallel electrodes, and you can apply a DC or AC voltage to that and see how the current flows in and out of the material to determine the permittivity. A more complicated method is shown in this diagram, which is a resonant cavity method. This uses a resonant cavity that has a particular resonant frequency with a given input frequency or RF frequency. And then when you put the sample that you care about in that cavity, that modifies the resonance frequency, and you can relate the variation in the resonance frequency to the permittivity also. With that, I will say thank you and turn the time over for questions.
Excellent. Thank you very much for such a detailed and informative presentation, Justin. That was excellent. Thank you.
Thanks.
All right. So now we can begin the Q&A portion of this presentation. So starting out with the questions in the queue, we can go ahead and start reviewing the questions we've received. The first one is, what is the impact of breakdown shown in slide 13?
Okay, oh, sorry, let me pull that back up. So electrostatic breakdown is kind of the thing we want to avoid. And I guess I probably don't need an image, but yeah, so electrostatic breakdown is when the field gets larger than a certain threshold, the electric field, you can experience electrostatic breakdown. And that is basically arcing. So if you have like static electricity, that's an example of electrostatic breakdown of the air. In a spacecraft, this is important because when ESD, that's another electrostatic discharge, when an ESD event occurs in a solid material, that usually involves damage to the material. So you get a brief high amount of current that flows through a small area, and that heats up the material and can melt it, and it can produce a local site where the conductivity of the material changes. So after that breakdown has occurred, you can end up with a point where more current will continue to leak through that location. And it can be kind of a point where further breakdowns branch off of that and can spread damage further into the material. Another reason it's a big issue is if you have sensitive electronics, that arcing can exceed the amount of current that is supposed to flow through a particular device. And so you can damage diodes and transistors in a computing device and basically fry your computer. So yeah, it's definitely this is one of the main reasons that we study spacecraft charging, is to minimize electrostatic breakdown and avoid those types of events.
Okay. Next question is the cobalt-60 radiation source used in testing to generate the radiation-induced conductivity?
Um, I I don't have a ton of experience with doing those types of tests. The ones that I've seen before, they did at Idaho National Laboratories with one of their um, radiation sources. But I think it probably any type of source could be used as long as it's ionizing radiation and you can control the dose rate. Yeah.
Okay, next question is, can you talk about some of the test results you had with different types of materials and recommend some of the better ones for a shield?
Um, let's see. I It's kind of interesting. So my background, I'm more of a uh materials testing kind of person. So um I have been mostly in charge of determining what those material properties are, making the decisions of how they're applied is something I haven't ever been involved with. Um, in terms of shielding, I think, well, first of all, the less insulators that are exposed to the outside environment, the better. So, um, but there's sometimes where that's not really possible, like with solar panels. So I guess I would say that I don't really have enough experience to say what materials are best or worst, and it all depends on what the need is. Like usually the materials are picked for some other purpose than as a ESD shield or um, yeah. Sorry, I don't have much more for that question.
That's all right. We have another one here. So, from your testing experience, is it possible to have different layers of material bonded and strong enough to allow for the use of untested commercial parts?
Um, I wish I could ask and talk to the people that are asking these questions. I th I don't know if they're asking specifically like or related to the rad hardness topic we talked about earlier. Um, but sorry, I need to see the question again. Um, is it possible to have I guess I don't really know the answer to that question.
I know that Nicole is still on the meeting. So, Nicole, if you can hear us, perhaps you might have some insight for that last question. Is it possible to have different layers of materials bonded and strong enough to allow for the use of untested commercial parts?
Uh, in the context of shielding, is that
I
part of the
believe so.
question? So shielding's an interesting thing for radiation in that you can really shield for dose effects, so TID, total non-ionizing dose, but not shielding actually affects single event effects in probably an unanticipated way, in that it changes how particles it changes the LET spectra that a device will see, but it doesn't really reduce effluence, if that makes sense. So even if you're, if you're trying to shield to mitigate single event effects, that generally in practice doesn't really work, only for dose. And you can use different combinations of things to shield. A lot of people use aluminum, or you can use smaller bits of tantalum. But as far, I've seen people use sacrificial layers of other things. But yeah, it kind of can vary.
Okay, maybe as we go forward, we can tackle some of these questions collaboratively.
Okay.
So, next one is, how would you know which kind of testing is needed to characterize materials? Do we have to do all the testing to characterize materials fully? Or I think what this person is getting at is there a priority list that you can set for the material characterization tests that you've discussed, JC?
Yeah, so I'd say with like if you're wanting to know these specific properties so that you can perform a computer simulation, I'd say the most important properties are the conductivity, the dielectric constant, and um, the electron yield. Uh, those three would probably get you pretty close to the right answer in your model. Maybe you could add proton yield, which is a type of ion yield that is also important. Um, yeah.
Okay. There's another question here. So, if the radiation induced current can flow through or into the spacecraft body, does it mean it's not a good idea to connect the electrical ground of a board to chassis? Maybe that's a question that Nicole might have some thoughts on as well.
So the radiation induced, like if it's related to conductivity, usually the radiation induced conductivity is a good thing. And that current always flows in a direction that reduces the amount of charge that's built up. Um, so all it's doing is modifying how much free charge there is to move around and try to dissipate the um, the trapped charge that's been put into the material. So I don't really um, I think that usually the chassis ground, which is kind of a arbitrary ground, but is probably still a good thing to be attached to, just so that you can have a well-defined reference between different parts of your system. There might be some applications where you want to leave something floating if you are worried that it could behave poorly with other things if it gets charged. But I think for the most part, you'd probably want to connect to a common ground.
Yeah, that makes sense. So we have another follow-on question, I think, related to the material characterization tests and your answer about the incorporation of simulation. So, what's the output of this kind of simulation? How do you correlate that data with test data?
Yeah. So in a simulation, you can look at basically any property you care about at any point inside of the spacecraft. Um, so For example, the types of sims that I frequently have ended up doing, I would look at, for example, the deposited charge density inside of a material, or the total ionizing dose and that depth profile in a material, and then the surface potential or electric fields inside. And if you're doing like a full environment simulation, that will tell you what will happen in the space environment. And then you want to look to see if the internal fields that build up inside of a material ever exceed that breakdown threshold. And if so, how quickly that happens. Um, if you want to correlate that to testing data, then you would need to probably simplify the simulation a bunch and recreate a scenario that you can duplicate the in the lab. So for example, you can try to pick fluxes and energies with the electron sources that are similar to what is in the actual environment that you'll see. And then in our in our test setup in our lab, we are able to monitor like the surface potential as long as we have a large enough area of the material. And so we can correlate that surface potential in our chamber with this well-specified uh, flux that's coming in, and we can correlate that to a similar sim that we run on the computer with the same inputs.
Okay, great. We do have a few more minutes left in the Q&A portion of the session. So in lieu of some more questions from the queue, I do have a couple for you that might muster up some more interesting conversations. The first one is, can you explain how to neutralize a sample when you perform electron yield measurements?
Yeah. So yeah, I have previously talked a little bit about how measuring the yield of insulators is difficult. And I mentioned that we use a pulsed gun to reduce the amount of charge that we're depositing in the measurement. But then between those measurements, we need to use some sort of neutralization technique to extract or to modify the surface potential back to a grounded potential. And the two methods that we have used that work are using a low energy electron flood gun. So you can just sputter the material with low energy electrons, and that will, if there's a positive charge buildup, those will be attracted to the sample until they neutralize that charge. And then we also used a UV source. So similar to like when I was talking about the photoelectric effect or the photoelectrons, um, if you irradiate it with deep enough UV light to start producing photoelectrons, then you can use that to remove negative charge that's been deposited in the material. But it's still an issue. Like there's it's hard to find high enough flux UV sources that are adequate to remove the charge, and some materials that work function that I mentioned is really large, and so you need to have a source that is deep enough UV that can still excite electrons out of those types of materials.
Okay. And another question for you is, if you wouldn't mind, could you comment some more on cathodoluminescence and why that's an interaction that might matter in spacecraft design?
Yeah. So when I've studied this in the past, it's been usually for space-based observatories, so telescopes, and they want to make sure that their spacecraft uh, isn't glowing brighter than the thing that they're looking at. So we've done tests to see under similar fluxes that they would be experiencing how much light comes off of the different materials that a spacecraft is made out of. Then they're able to take that data and determine if it's bright enough to matter in their application.
Okay, great. So seeing no more questions in the Q&A, I think it's appropriate to conclude the final presentation of this session. As a reminder, following today's webinar, all registrants will receive an email from EMA with a copy of both presentations from today's session, as well as a link to the recording of this presentation. If you have any questions about a particular section of interest to you, please feel free to reply directly to that outbound email or reach out through the ema3d.com website. So next up, please look forward to the upcoming keynote address led by Dr. David Pomeranke from TU Graz in Austria. He will be focusing on electrostatic discharge and its simulation in ANSYS Charge Plus, and that session will begin on July 1st at 11 a.m. MST. Thank you all very much for your time and attention, and we hope you all have a great rest of your day. Thanks again to our wonderful speakers, presenters for today's session, and we'll see you all again very soon.